Welcome to the session. My name is Zhang Kai, and I work as cloud architect for Nokia Enterprise and Service Cloud. We're talking about the building managed bare metal class Kubernetes service at scale with 100% open source software. At first, how many of you are here are building or operating using bare metal Kubernetes cluster? Okay, many of them. Okay, very good. So about background myself. So I joined the NESC. We call the Nokia Enterprise Service Cloud as NESC in short. So I joined the team since 2019. Now I'm working as a workstream leader for the Nokia Kubernetes service. In the past, I have been a cloud architect for cloud platform based on OpenStack and the VMware softwares. Also technical support and system engineer, network engineer before. Then what is NESC? Nokia Enterprise and Service Cloud. It's probably one of the world's largest corporate private cloud offering infrastructure as a service. So we have globally 5 data centers plus 4 edge locations. So from compute CPU capacity point of view, we have around 920,000 virtual cores. And that translates to around 12,000 servers in 350 racks. On top of that, we have around 230 GPUs supporting machine learning AI use cases. 1/3 of the CPU capacity, they are deployed as the managed Kubernetes clusters. We have right now around 420 managed Kubernetes clusters. So some of them are virtual machine based. Some of them are bare metal based. And our largest Kubernetes cluster on bare metal has 12,000 virtual cores or 112 servers at the moment. So, and another big part of the capacity, we have OpenStack for virtual machine workloads with more than 6,000 projects. Also, we have the Ceph-based storage providing block and S3 service. At the moment, there are more than 70 petabytes data. So we build everything from open source, and there are some logos here. I will go through some of them. We choose for building the bare metal management Kubernetes services. Incoming slides. So this is the Nokia Kubernetes service. We call this NKS to provide managed Kubernetes clusters. So this is the private cloud, and the customer is the internal R&D team to support our software and product development activities. And there are 3 layers, and NESC manages the infrastructure and the Kubernetes layer, and users manage the application by themselves. So from infrastructure layer, we have compute powers from virtual machine on OpenStack or bare metal, which is the full focus of the session today. On the side, we have Ceph-based cloud storage and network providing connectivity. Kubernetes cluster layer is a typical combined with control plane workers, and for bare metal only, optionally, there's the GPU worker as well as an option. It has a pre-integrated load balancer service, CNI for port networking, CSI storage plugin for persistent volume support. Also, there's a pre-integrated monitoring logging system from OpenSearch, Prometheus, and Grafana. So then let's talk about the journey to the managed bare metal service, Kubernetes service. So before we start this, we have already a virtual machine-based Kubernetes service. But there are more and more demand from the customer. They want to have a very big sized cluster And having that on virtual machine it doesn't fly. There are too many VMs, or some VMs are too fat. It's not that efficiency with the hypervisor. And also from the performance point of view, the bare metal performs better. We don't have to go through the hypervisor. So then we start from scratch to design this new bare metal based Kubernetes service. We set some design principles. So we want to be using fully open source software. And we try to make a unified single server pool per data center. The servers can be consumed by any cluster from any rack. We want to break the rack boundary, which was the limitation factor for forming the clusters. There will be more detail discussing that in coming slides. It has to be API driven, enabling automation. So any manual operation at our scale is a no-go, since we have too many server at racks. So automation is a must. A modular architecture to avoid technology and solution locking, which guarantee we can swap the open source component with minimum effort. And it has to be Kubernetes native and a security built-in. Those are reflected in the OS choice we will go through later. So this is the infrastructure prior to the bare metal service. As I said, before that, our majority computing power are installed as OpenStack Cloud. And the whole infrastructure and network fabric was initially designed for that. And the whole fabric was fragmented into cloud. Every cloud has kind of a mini fabric, and inside it there is a huge layer 2 broadcast domain across the racks in one cloud to support the floating IP. And there's layer 2 here and there on different layers. There's layer 2 on the server side, on the switch, top of rack, and the spine switch side. Without changing this, we cannot achieve our target to have a single unified server pool for flexible allocation of the servers. So we built something new. There's a new fabric with layer 3 routing only. So we get rid of the layer 2 from any place. There's no layer 2 at all in any place. So all the connections between two components are end-to-end, point-to-point connections. BGP routing is running between any two connected endpoint. That requires us to run the BGP routing on the host. More detail on that in coming slides. We have also MetalLB running with BGP mode, providing the Kubernetes load balancer service. By doing so, we can have a server pool across multiple racks, since every node is a BGP speaker independently. That also brings the benefit of the IP. IP become portable. We can have a common IP pool. The IP and server together can be allocated on demand and released on demand. For example, we can create a cluster taking servers from any rack and also allocate IP from the IP pool for every server. Do similar thing for next cluster and for the third. And the scaling becomes also easy. If we, for example, want to add a new server to cluster 2, we just allocate one server to the cluster and allocate one IP to it. That's it. And resource releasing becomes also easy. If we want to delete, for example, the cluster 3, we just delete the cluster, release the node, release the IP. So the IP go back to the resource pool, server go back to the resource pool, waiting to be allocated next time. So that breaks the boundary of the racks. So we can forget about the racks. There's no limitation from the racks. So we only talk about the server. To achieve that, we need to run the BGP on every host. That is achieved by running FRR as a container on every host, which pairs with two leaf switches by using BGP unnumbered through the IPv6 link local address. That simplifies the configuration and also saves the IPv4 address. And every node has a allocated /32 node IP, which is advertised by the FRR to the fabric. On control plane node, there's another /32 IP running on another dummy interface, advertised through the FRR as well. Every node aside also runs a MetalLB speaker from the daemon set. So MetalLB locally pair with FRR through a virtual Ethernet pair. So the Kubernetes load balancer IP get advertised by MetalLB to the FRR. FRR further redistribute it to the fabric. And to bootstrap the cluster, we need to set a /31 IP range for first interface, ETH0 here. That is used to PXE boot the server and get OS installed. But that is used only during bootstrap. During the runtime, the BGP routing is the only network we have here. We try to simplify the hardware configuration. So our server recent spec, we have a single socket server, but it supports also two CPUs from Intel or AMD, and we have this 6:1 memory to core ratio. Every virtual core has 6 gigabyte memory. A single NVMe disk with 7 terabyte or larger, no RAID controller, and 2 times 100 gigabit Ethernet port connecting to both leaf switches for redundancy and bandwidth sharing. Since we rely on Kubernetes redundancy or self-healing features, we don't have to provide so high redundancy from hardware layer. So it can be, the worker node can fail, and we just take them away, fix them, and add a new one from the pool to replace it. We have even automation to do that automatically, to automatically detect the failed node and replace it automatically by taking the server from the pool. And that makes sure we have the server will be vendor agnostic, and any commercial off-the-shelf server should work as long as they support standard IPME interface over network, which we use to control the power and configure the PXE boot. And it has to be supporting the Redfish management API to automate the BIOS BMC configuration. So those servers from those mainstream vendors has been working fine without problem in our data centers. So OS choice, Talos Linux was chosen for reasons of its immutable and the minimal footprint, and it's purpose-built to run Kubernetes only. It has security building, with read-only file system, no SSH shell console, only 9 binary from the OS. And it has CIS Kubernetes guideline applied by default. So it is managed by API and by API only. API is the only interface you can talk to it. that brings the easy automation for operations, and it has declarative OS configuration, which showing on the right as example. In YAML file, we can define the installation disk, installation image, network, blah blah blah. So this is very easy for us to automate the installation and later the patching of the file and upgrade. By the way, anyone is using Talos Linux here? 1, 2, 3, 4. Okay, only 4. Okay. But I would encourage you to try it out if you haven't heard it or tried it yet. And deployer. So Talos API, but anyone is using Talos API, a cluster API. Okay. Other users than Talos users. So for people who are not familiar with cluster API, so it's a Kubernetes way of managing the life cycle of the user Kubernetes clusters. It provides a declarative way of configuration to present a user cluster as cluster API CRDs. And since it's a Kubernetes way, we need a management cluster to run them with several providers for Bootstrap, infrastructure, and control plan. And Talos provide all of them, so naturally we use those to deploy Talos-based clusters. And every user cluster, they are modeled into their own namespace, and which contains those CRDs, including cluster, infra cluster, and control plan, and machine deployment. Each of them represent control plan machines and the machine and workers. So each one has a replica. It works like kind of deployment with replica. You can set to scale them, and every machine represent, in this case, is a bare metal server, which is bootstrapped by the Bootstrap provider and installed by this provider and also operated by them. To achieve the single server pool, we need an inventory. So Netbox is used to serve as a source of truth for data center resources and IPAM tool. So there we document information about the site, rack and devices, cable between those devices, and IP prefix and addresses, and tenant. A tenant is a grouping of the resources. And here in the background screenshot, it's one tenant. And one tenant here represents one user cluster, one managed cluster, which has collection of resources allocated to it. Here shows 7 devices, which means 7 servers, and several IP prefix and IP addresses. Netbox has REST API available for us to programmably allocating servers and resources from the pool. And we have the abstraction layer API in front of them to do those in batches. Several infrastructure tools we use Ansible AWS as the automation engine for the data center operations and the configuration tasks, like switch and the DHCP configuration change and backup schedules and more. We use Kia DHCP server to provide DHCP services for DC devices like server, BMC, power distributed unit, and so on, and also switches, for example. And it also provides the PXE boot support for server bootstrap during the installation. Secret management. So HashiCorp Vault is used, It has a secret store for storing those Kubernetes cluster access credentials and the Talos host API access credentials, DC devices credentials like switches and more. In the management cluster, we use the Kubernetes external secret operator to sync the Kubernetes secret with the secret in the vault. That secret I'm talking about is mainly about the BMC credential of the servers, which will be used by the cluster API operators to control the power of the servers, for example. In the management clusters, we integrated Vault Kubernetes secret engine to generate dynamic credentials for the user to access their own managed Kubernetes cluster. And we went through those components, open source component, and here is the workflow example to showcase how they work together to do the end-to-end provisioning deployment of a bare metal Kubernetes cluster. We start with the Netbox, which serves as a server pool from the data center resources. And we build a abstraction a layer DC resource API in order to get requests, for example, from the deployment tool. We call it Ncase API. It could call the API like, I want to create a new cluster with certain number of server or certain number of cores, and the resource API then go to Netbox and look up free servers from the pool and pick up the free servers, and allocate them and make the modification in the Netbox as an allocation. Then it calls another abstraction API for our SDN, for our network. That one goes to Netbox and allocates the IPs from the pool for every allocated server. And in order to make them working, it calls the AWS job to configure the switch. So by default, all the servers are powered off and the switch ports are disabled. So they are totally like if they are unallocated state. Once they are allocated, we need to enable those server-facing port on the switch and also configure the BGP peering configuration and configure the DHCP relay on those switch ports. That is done by the SDN API here through the AWS job. And after that, resource API call another job, AWS job, to configure the DHCP to prepare the PXE boot for those allocated servers. Then after all the data center resources are ready to work, then it returns the list of allocated server with IPs back to the deployment tool. As we said, Cluster API is the deployer, and it has declarative CRDs to represent the managed cluster. So with that input, the deployment tool can create those Cluster API CRD templates. And to deploy them, just to apply those templates to the management cluster where Cluster API is running. Cluster API providers will further process those and model the cluster there in their own namespace, and then it try to bootstrap it. And to bootstrap them, the provider need to access the BMC interface to power them on and configure them to boot from the network through the PXE boot. So it does that. It gets the credential from the vault, then it bootstraps the server, the server does the PXE boot from the DHCP server we configured earlier. And after that, the provider continue to install the Talos OS image there and push those machine config into every node. That enables the Kubernetes software installation. So at that time, we have a Kubernetes cluster up and running. So this is the workflow example to showcase how all the components are working together end to end. And I think my presentation will end here. We have 5 minutes for Q&A. Please. Thanks.
So after this stage, there's a cluster that kind of is exposed to the client. So it's their job to kind of integrate to wherever GitLab and like what other operators they need and what they want to do. So it's like you provide kind of the empty platform at that stage, or do you have kind of more configuration for the
Yes. Yeah, this is not mentioned in this workflow. And after the empty cluster is up and running, the deployment tool will continue to integrate to pre-configure some other things. The MetalLB, of course, is already, I told it will be pre-integrated with the subnet pre-allocated. User can use that to create a load balancer type of service with an external routable IP. It also does the storage integration. So we have the self storage. So self storage will be CSI will be configured with RBD at the backend. So the service storage class will be configured for them to use for the PVC creation for persistent volume. Also, we will pre-install some monitoring component for log collection. We have a central logging system. There's the integration there, so they will get a credential how to access that in the notification of the cluster creation. There's also a Prometheus monitoring configured locally. So in the end, they will get, for example, they will get an email including how you access your cluster, and the URL of the login system, and the Grafana and alert manager URL and the credentials, how to access them, and that is what they get in the end. Then on top of them, it's up to them to how to deploy the application or integration with other stuff.
Where do you run the management cluster?
Sorry, can you repeat the question as well?
Where do we run the management cluster?
Yeah, like where does the cluster API run?
We have a management cluster. So
That's also bare metal.
it's a bare metal. So in every server pool, we run either 3 or 5, depends on how big the data center is. So we pick 3 or 5 server to run as a management cluster, and there, the cluster API is running there. Also, this deployment tool, DC resource API, SD API, they are all running there. They serve as a management plan for the whole automation.
You're running MetalLB. The Cilium has a gateway BGP for some time now. If you're using Cilium, is there some reason you have?
We are using Cilium for as a CNI, but not with BGP.
Have you looked into it for any reason not to use it? Or?
Initially, it was there, and we picked the MetalLB at the time. That is looks like the only available option at that time. And Cilium has BGP support added later. We haven't looked into that if it's working the similar way as MetalLB, but this is one option we may try in the future.
Yeah, it's pretty much same.
Yeah. Yeah. Even MetalLB, I think, MetalLB has also they are also like changing over time. They have their own speaker implementation. Later, they also support FRR as speaker in the background. We are still with their native mode. Since our architecture is quite simple, so we only need to pair with local FRR. We cannot use the MetalLB or whatever speaker to pair with the leaf because FRR locally is pairing with the leaf. We cannot have another pair also pairing with the leaf.
Yeah,
So that's why FRR is running in between.
yeah, Cilium will also use a FRR, or I've even had it running on OpenBSD, BGP. So
Mm-hmm.
to,
Okay. Okay. Is there? Yeah.
Yeah, question about the deployment tool and the target. How long does it generally take to provision a new cluster?
Around 10 minutes in total.
I
The
believe it highly depends on the number of computes.
the provisioning is run in parallel, so number of compute it doesn't really matter. So they are running all at the same time. So the
Even the
big
masters and the workers.
yeah, of course, master and workers are provisioned at the same time. Of course, some dependencies. A worker can join the cluster only a control plan is up and running, but it will keep retrying. And the most time-consuming environmental server is the booting. We have to boot like 2 or 3 times, I think. First time is to do the disk wiping, to clean up the disk. The second run is to boot into the staging OS. From there, we run the installer, Talos installer, to install the real OS to the disk. Then the last boot is boot into the actual OS. So sometimes bare metal boots very slow, so that is the most time-consuming part.
Maybe a follow-up question to that. If you mentioned that bare metal server booting is slow, Talos Linux is capable of doing KExec booting, so especially like after the installation,
Yeah.
you just KExec into the
Yeah.
newly installed system. Does that work on your hardware?
Yeah,
or do you
yeah,
use
yeah.
the
It works. It works. So.
Yeah, so it should be
By
that model.
by help with that, I think only first boot takes most of the time,
Yeah.
and after that, from the staging to the actual OS, it goes through that fast KEC boot. Yes. Also, upgrade is doing the similar
Yeah.
approach.
Can we take one last question?
There are many components involved. How much error handling do you have? Like if it failed somewhere in the middle, will there be provisioned servers registered in Netbox, but there's actually no cluster, or do you have error handling there?
Yeah, very good point. Yeah, that is the pain point we went through in the beginning of this time. We started like 5 years ago, and we keep improving the workflow. There are so many components involved between them. They have API calls between them so during the journey there are many cases like a timeout between this component and that component. We have to keep improving the error handling and add retry, increase the timeout kind of thing. So to make it more robust over time.
Okay, thank you
Okay.
so much.